Okay, so we want to start the last lecture for today, BrainInTheLoop for AI Training and Validation by Sergey Vaisman from InnerEye.
Thank you. Thank you for staying for this late hour. I guess the organizers kept the best thing for the last. So today you're going to learn how to use your brain to generate labels and train and validate AI models, how to do it fast and also reach higher performance. So I'm Sergey Vaisman, VP R&D of InnerEye. A few words about our company. We're a startup created by a technology spin-off between Ben Gurion and Hebrew University a few years ago, with the main idea to combine neuroscience and machine learning. And we believe that in order to create better AI applications, we should combine human intelligence with artificial intelligence. And our way to do it is by establishing a connection between the brain and the AI model. And we believe that any AI based application should not ignore the human brain and use it as one of the sensors on the processors of the application. So our brain actually is a very powerful instrument, and no computer today can actually do amazing things that our brain is capable to do, and specifically to process huge amounts of new and very complex information and do it in such a short time. So actually every time we see something new or practice, our brain sends messages along certain pathways of neurons and establishing new connections. And this is the way our brain learns, and actually each one of us is different, and every time we learn something, our brain changes itself. So this is the main reason that all artificial intelligence applications today heavily rely on humans, on human intelligence. And actually every stage of development of artificial intelligence model, from data collection, annotation, as you can see in this image, selecting images for training, and actually designing and training the neural network, and even after the deployment, all the time new types of samples of images arrive, and we need to make sure that our model still performs the way we planned it, and to continue validate it. So all this process is known as Humanintheloop, but of course it comes with challenges, and I wrote here some of them. And the main challenge is huge amounts of unlabeled data, and this is a problem especially in areas requiring domain expertise like security, healthcare, quality assurance, and others, where the amounts of data are enormous and the availability of the experts is very limited. So that's why this process is very costly today, very not inefficient, and there are also privacy issues. Some of us don't want to expose the data to third parties to label them. So in order to address these challenges and to utilize the amazing capabilities of our brain, we developed the concept we call BrainInTheLoop, which is the iterative framework for training and validating of AI models that I'm going to present now. And using this framework, we are able actually to overcome most of the challenges, overcome the bottleneck of data, to improve the efficiency and also improve the performance, and you are going to see how it works. So just to keep you motivated, this is the performance chart of AI network we trained to detect sport cars.
Why sport cars? Because this is not an easy task, and actually you can argue which car is a sport car, and this is process that requires some thinking before you actually label the images. So we built a simple network, and we'll explain later, and trained it once using manual method, as we all know, labeling images, training, and so on, and then using the brain-in-the-loop concept. So just to keep you motivated, you can see, first of all, the advantage of time. So the same network trained using our method was able to reach even higher performance. This is area under the curve, and do it 10 times faster. So I hope you are thrilled to know how it works. And let's dive into the details. So this is the main block diagram of this framework. It includes three main parts. The first part is the human expert or user watching images, and as you may notice, the images are shown very fast. So in this case, it's only 3 images per second, but in several applications we're able to go up to 10 images per second. And this is possible due to the fact that we work only with the brain, and you will see how. The second part is the brainwave classification network. So we collect brainwaves and we classify them. And the output of this classification is what we call soft label, and I'll explain how we get this. And the third part is actually the network we are training, the model we are trying to create. And this is an iterative framework, so there are several iterations. The human user sees a subset of images, and eventually the network is converged and trained and is able to reach this performance that you saw before. So let's first explain what is this brainwave classification, because this is the most important part, and I want you to understand it. So let's tap into the brain, and you can see here the main process that each of us does when we see an image. So at first we are sensated, our eyes see this new image, new information, and actually transfer this information to our brain. The main part of our brain, the visual cortex, is used for processing of this visual information. After we processed it, we're ready to make the decision. For example, in this use case before, was it a sport car or not? And we plan the response. What we do now with the decision? We press a button, we tell someone, how do we label the image, and so on. And when we are planning this response, we are distracted. Because we want to do this motor execution, we want to press a button, we want to write something, we are distracted, we cannot process new information. And all this creates this bottleneck. Actually, this process shown above takes something like from 2 to 5 seconds in the best case, depending on the complexity of the image, while the visual processing and the start of decision making takes something like from 300 to 700 milliseconds. So actually, if we are able to bypass all this time-consuming part, we will be able to gain this time advantage. And additional advantage is that when using the manual response, we're actually losing the important information, the important part that happened here. So was I confident when I made the decision? Maybe I thought about something, I was distracted. All this information, we actually lose it. And again, if we are able to monitor it by measuring the brain activity, we will gain access to this information, and I will show that this information is very valuable. So How do we measure the brain activity? There are different ways to measure. We use EEG, electroencephalography. This is actually very well-established technology, originally used for medical applications. We're a software company, so we don't develop the devices, but there are a few examples of devices that we use. And each of the devices actually collects electrical activity of the brain. So in this case, there are 7 channels, 7 electrodes on top of the head, and each of them collects electrical activity. So when we see the image, our brain processes it, neurons fire together and create electrical potentials that we measure. So what we do with this information? Let's go back to the fast presentation of images. You remember that in this example, we showed 3 images per second. So for each image, for each presented image, we can actually synchronize the presented image and the collected EEG response. So for this first image of this red car, we look at a time frame of something like 1 second, because remember I mentioned that the process in the brain happens something like up to 700, 800 milliseconds. We look a bit further, and we take this data. We call it single trial spatiotemporal matrix because it's time samples multiplied by channels. And this is the input to our brain classification network. So we want to know what happened in the brain as a response to the image that the brain was shown. Additional way to look at this information is by putting all these trials one after another. You can see in this example something like 10,000 trials, one on top of the other, multiplied by 7 channels. And the reason to look at this in this way is that if I show separately the response to targets, for example, sport cars, it can be any other applications, detecting defects in manufacturing, detecting suspicious objects in luggage and so on, you can see that there is a difference that happens, again, something like 200 to 700 milliseconds. The bluish colors here indicate low potential, and yellowish colors indicate higher potential. And you can also see what happens in spatial response in the brain. So you can see there is a difference between targets and non-targets. And this difference is something that we are looking for, how to differentiate between brain responses to targets and brain responses to non-targets. Now, if we average all these responses, the difference is very clear, okay? But in real applications, we cannot average responses because we want to know the response in real time to every single image. So this is just to illustrate what we're looking for. And of course, the data is very noisy. The brain does not send us clear signals. We need to apply different signal processing methods and especially classification. So we use deep learning to classify brainwaves, actually to address the variability in different brain responses and be able to cope with this noisy data. We use ensemble of different networks, different classifiers, and the output is classification score. So the input is brain response to a single image, single spatiotemporal matrix, and the output is the classification score. You can see in this example how this the example of distribution of this score. So for this data of cars and sport cars, some of the images got high score, some of them got lower score, and you can see that most of the sport cars got higher scores. and you can put a threshold somewhere and set operation point of this classifier. So for this particular threshold, for example, it will be able to reach 100% true positive rate, but some amount of false alarms. And we will see later how we deal with these misclassifications. So now when we understood the concept of how we use the brain to classify images, I want to introduce the concept of soft labels. And let's imagine you want to create an AI model to classify images and detect images of flowers. So I want to train the model and tell what is flower and what is not flower. So all these images, by the way, taken from a Google Open Images dataset, have label of flower, and I think you will agree that none of them should contribute equally. And the question is, can we create more informative labels? This is one of the main ideas of this brain-in-the-loop concept, that every image actually comes with what we call soft label. So how we create this soft label? Actually, very simple. We take the classification score that we saw in the previous slide, and we create a weight. So if the score was either very high or very low, it means the weight will be high. If the score was inconclusive, something in the middle, the weight will be low. And this is the way, so the soft label is actually the usual label generated by putting a threshold somewhere and a weight. We wanted to make sure that this soft label actually is correlated with the confidence level of the user. So we checked response time, and you can see that for images that got low response time, meaning the user was confident before he took the decision, the soft label was also high, and the more the response time was slower, the user was less confident, the soft label was lower. Okay, so now when we understood how we create the soft labels, let's see how we use them and how the iteration framework works. So of course you can train any network. In this example, we took the VGG16 network and added classification layers in the end, and these are the layers that we're training using the soft labels. The way, our way to transfer the information from the brain to the network is by adding this weight, the soft label, as a sample weight in the loss function. So in this way, it's in this case, it's cross entropy loss function, and we just multiply it by the sample weight we generated from the brain. Now, after each iteration, we check the convergence of this network. It can be done by several ways. We just check the prediction of the network for each sample, and we take only the least confident samples to be sent for human review for next iteration. So in this way, this is actually active learning idea that we utilized. So in this way, the human user will see only a subset of images, and specifically we'll see a subset of images that the network trained on soft labels was not confident in. So this is the idea. Just to make sure we did the right thing, we checked several things. So one test that we did was to take these soft labels and to permute the weights. So we wanted to see if this, if it's not accidental improvement of performance. As you can see, when we just permuted the weights, so we took the right label but wrong weight. So for example, sport car but low weight, and the opposite. And you can see that it misleaded the network that we're trying to train. While using the soft labels, was able to reach this higher performance. And as you can see, it converged pretty fast, using only a smaller amount of data. A second test was to see if this active learning approach actually helped using these soft labels. So we tested once using this active learning approach, and second using random sampling. And again, you can see that active learning combined with soft labels was able to reach higher performance on top of just soft labels with random sampling. So both of the components of our framework, the soft labels and the active learning, contributed to improving the performance. And you can see it as a feedback between the confidence level of the user and the confidence level of the model. So let's see the example of performance in this sport car example. So we started with something like 3,000 images of cars and sport cars, and we wanted to detect sport cars. And here, this is by the way the output from our product, our system. So after each iteration, we show what images the system showed to the user. So you can see it was 200, then 400, then it started to become lower numbers. And eventually after 5 iterations, after viewing something like 28% of the images, the network converged to the criteria that we set. And this is just examples of sport cars detected. And we did this test on several participants, and here are the examples. So you can see that this every test was done on something like 50 different runs, and you can see here the standard deviation. And you can see that for all participants, the performance improvement was consistent, especially reaching high performance after a lower amount of data. And if you translate the amount of data into time, you get this time advantage that I showed in the beginning. And I want to emphasize that this time advantage is composed of three components. So one is fast presentation of images that you understood. We show, in this case, 3 images per second. The second is using the soft labels. So soft labels actually distill the main important information, and that's why after smaller amount of images, you're able to learn better than using usual method. And the third is the active learning approach. So the user doesn't need to see all the images. It reviews only the images that the model was least confident about. And now we can go back to this chart I showed you in the beginning and see it again. And I hope everyone understood how we were able to reach this performance. Okay, so for the end, I want to mention a few additional use cases of this technology of combining brain with artificial intelligence. So first of all, I presented here example of binary classification. And of course, all of us will be interested in multi-class. So it's not so easy with the with the brain and EEG, but this is something that is feasible. And we did the example using these 4 categories, 4 classes of vehicles, plants, buildings, and dogs or pets. And you can see here the average brain response of all these categories on one single channel, one electrode. So remember that there are at least 7 like this. So you can see that there is a difference. So there is a difference, and meaning that separation of categories is possible. And when we tested the classification accuracy, actually for houses, pets, and vehicles, it was quite high. For plants, it was less good, but average accuracy of 81%. So this is encouraging, and means that classification of several categories and not only binary may be feasible. Additional use case you can imagine is the validation of annotation quality. So if you have already some kind of automated labeling, semi-supervised approach, you have already generated labels or bounding boxes, and you want to validate the quality of the data. This is also something that we tried to do using our system. You can see here on the left side example of all the images that were classified as flowers, but are mainly not flowers. And using our system, we were able to very fast detect these images, so it can be applied, for example, any application like quality assurance in the factories. You can very quickly find the defects or filter out the false alarms of automatic detection. Additional use case, and this is actually something that we have a product, so we're using it already in airports. So in this case, we already have the computer vision network that was trained to detect prohibited items in X-ray images. And we have a human expert. So in airports, this is the security agent sitting and looking at X-ray images of your bags when you fly. And he needs to find the prohibited items, explosives, guns, knives, liquids, and so on. So when we combine, we have this architecture that combines inputs from the brain and from the image itself, and combines them at the feature level. So we are able to show that this combination is able to improve each of them separately. And so for any application, when you still need a human expert, and in airports this is required by regulation, but you want to improve the performance, this product can help. Additional idea that we still not tested, but it might be interesting to explore, is applying the same concept for reinforcement learning. So in reinforcement learning, for example, in training of autonomous cars, there is an agent that gets a reward. And if, for example, the driving was without any accidents, the reward will be positive. But this method actually does not take into account some situations that might happen on the road. And for example, in this case, you can see there is a pedestrian crossing the road, and eventually everything was fine. This is the simulation, but in our system, you can actually collect brain responses to this particular scene. For example, you can see that we monitor a hazard of the user who sees this image. So this kind of information can be used as a state or reward in reinforcement learning framework, and potentially improve the performance of the agent. So we are good on time. Summary slide. So I presented to you the concept of brain in the loop, how you can use your brain to establish a direct interface between the human user and the AI model. We showed that using this model, you are able to overcome the challenges we discussed in the beginning. You can reach 10 times faster performance. You are able to reach higher area under the curve. You're using this approach, you can use your own experts and keep your data private. You can also personalize your AI model based on your expert, or especially happening in healthcare. So each doctor may have his own view of data. Most important, you create a real-time interface. So this interface can work in also after the deployment and continue to validate and improve your AI models. So thank you, and we have time for questions.
I have two questions. The first question, I do not understand how the first network that looks at the brainwaves and gives a classification score, how was it trained, on which targets, and what it is for? And the second question, maybe more interesting, is did you try to quantify the difference if the spectator is concentrated, or maybe just staring and maybe daydreaming? Can you still get good results?
Yeah, so thank you, very good questions. The first question, indeed, I forgot to mention that this network first needs to be trained on each specific user. So each one of us is different. So our way to do it is, we call it creation of user profile. We show a set of labeled images to the user and collect brain responses. And now, due to the fact that we show images fast, so very fast you're able to collect a lot of data. So after seeing like 10 minutes of seeing images, you're able to collect several thousands of brain responses. And of course, this is the initial process. After that, in our, for example, in our airport application, we continue. Yeah, so the brain network classification is supervised. At first, you need to collect labeled brain responses. And the second question, yes, so this is actually a problem when you don't know what your labeler, was he concentrated, was just staring. So due to the fact that we actually monitor the brain waves, enables us to monitor the attention level of the user. So we do have a feature that actually is able to tell you if the user was just staring at the screen or his brain already started processing the data. And we do see that if the user didn't process the data, his performance will not be good. So we cannot trust it. Our way to handle it is just to detect it and show this image again.
Two questions. Is the user aware about the label that you are looking for, or just staring images without knowing about the category, anything?
So the user needs to know what his task is.
Okay.
So if the task is to detect sport cars, you need to do.
So the second question, did you compare with just shallow network that will give you the weight without any human in the loop?
Could you repeat?
I mean, did you compare your system with just taking a shallow network that will give you the weights rather than the human information?
Yeah, so we did first this test, and actually this approach can also reach good performance, but in some stage it will reach saturation because it doesn't get new images from the human user. And also it depends on, I think, on the complexity of the task. So for complex tasks requiring human expertise, this will not reach the same performance as the human expert.
Okay, we'll take one last question.
Yeah, so did you measure what happens to your, I don't know, test subjects, users, whatever, after prolonged exposure? Did you feel a Helsinki? I mean, doesn't this affect the human brain?
Yeah, of course. So one of the, our concerns was to make sure that the user are not feel comfortable after that. So we did a lot of tests to establish what is the optimal time for being able to use the system, and the main limit is not putting the electrodes. It doesn't do anything to the brain. It's completely passive device. It's just watching a lot of images. So this is a bit. This is more higher cognitive load than usual, but we developed, a protocol, you can call it. What is the optimal way to work with our system and make a break and continue? So we tried it. So our system was tested on something like already 200. Real users, and up to date we didn't see a problem.
Okay, thank you again, Sergey.
Thank you.
And thank you for participating in AI Week.